This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software. As a software engineer, chances are you've crossed paths with MongoDB at some point, whether you're building an app for millions of users or just figuring out a side hustle. As the most popular non-relational database, MongoDB is intuitive and incredibly easy for development teams to use. Now with MongoDB Atlas, you can take advantage of MongoDB's flexible document data model as a fully automated cloud service. MongoDB Atlas handles all the costly database operations and admin tasks you'd rather not spend time on, like security, high availability, data recovery, monitoring, and elastic scaling. Try MongoDB Atlas for free today. Visit mongodb.com/cloud to learn more.
This is Nate Black for Software Engineering Radio. My guest today is Boris Cherny, the author of Programming TypeScript. Boris is the organizer of the San Francisco TypeScript meetup and is a software engineer at Facebook. Boris, welcome to Software Engineering Radio.
Thanks, Nate, for having me on.
I want to start with just talking about what TypeScript is at a high level. What is TypeScript?
TypeScript, it's a really, really weird language that works exceptionally well in practice. Unlike a lot of languages, it's compiled, but the compile target is very high level. So it actually compiles to JavaScript. It has a really cool type system. You can describe the type system in a bunch of ways, but I guess at a very high level, it's structural, static, strong, mostly inferred, and gradually typed. The gradual typing part is also pretty unusual. There's maybe a small handful of languages around that are gradually typed. It's really a thing from the last 10 years or so. I think TypeScript is the most successful out of those, at least so far.
Is TypeScript popular, or how does it compare to the alternative compile to JavaScript options that are out there?
It's surprisingly hard to come by numbers. There's this survey called State of JS. It seems like it's grown something like 50% year over year. And if you go by NPM, the downloads have increased something like 3 times year over year. Overall, if you're looking at the space of compile to JS languages, which is a really interesting space, and I think it kind of deserves its own conversation about why are there so many compile to JS languages, TypeScript is by far the biggest. So judging by the number of type definitions that are available for third-party libraries, as of a year ago, I think it was something like 10x bigger than Flow, which was the next closest one. And that's bigger than Reason, ClojureScript, Scala.js, all of these other compile to JS languages.
Why are there so many of these? Why is it needed to have a compile to JS language?
I think it surprised everyone how big JavaScript got. It's really the scripting language. And for some reason, now it can run on every computer, on every phone. You can run a little VM on an IoT device or on a Raspberry Pi to run it. It's so ubiquitous. So people have built these really big apps on it. Facebook has built some really big applications on it. Google has built really big applications on it. A lot of people really rely on JavaScript. But the problem is it's sort of a weirdly designed language, and it has a ton of different footguns. And it lacks some of these fundamental features like static types that people typically talk about as being necessary to scale a program across more engineers, more devices, etc. So I think people saw all these different thorns in JavaScript and all these different limits to scalability and try to solve it in all of these compile to JS languages. And the advantage there is there's this enormous space of devices that can already run JavaScript. So all you have to do is write something that can compile to JavaScript. And then it can already run in these devices. You don't have to convince people to install your VM or install a binary or anything like that.
Who created TypeScript, or who's behind it and maintaining it?
Yeah, so TypeScript, it's a project out of Microsoft. It's created by Anders Hallberg. It's the same guy that did C#. He also did some work on the Mono runtime. He did some other famous projects. I think there's also contributions from a lot of open source people. From Google. Google is a big adopter, so there's some contributions there. But it's mostly out of Microsoft.
Does that mean that there are some similarities to C#, or if a person knows C# or perhaps Java, how far away are they from understanding how to use TypeScript?
Yeah, I think it's pretty similar, at least as far as appearances go. I'm not a C# guy. I've written a little bit of Java, but I'm no expert at it. But at least if you look at the language, the syntax is certainly similar to C#.
Conversely, on the other side of things, how similar or dissimilar is TypeScript from JavaScript?
Yeah, so TypeScript compiles to JavaScript, and it interoperates really well with JavaScript. And that actually goes pretty far, actually, to the point where every valid JavaScript program is also a TypeScript program. It might not type check, but it will compile. So, for example, if you have a JavaScript file that ends with .js, rename it to a .ts extension, that's a TypeScript program.
How well does it work together with something like React or Angular?
It works really well. TypeScript works well with whatever framework you might be using. Angular is written in TypeScript. It works well with Ember or with Vue. My favorite combination personally is React and TypeScript, because with React you express the view as JSX, which is kind of this representation of HTML in your JavaScript. It's nice because this elevates the view code to values. And because they're values, that means you can now model it with types. And this is as opposed to these like older view systems, stuff like handlebars or these other systems where essentially your view is a big string and you use these templates to template in values. And the problem there is it's not really type safe. But because when you use React with TypeScript, because the JSX is a value, you can use TypeScript to make all sorts of assertions about it and prevent you from doing invalid stuff. So an example is, let's say you have an unordered list in your view and you have some list items within it. You can enforce that the only valid child of an unordered list, like a UL tag, is an li tag. And this is something that you get for free when you use TypeScript with React. I actually don't know if it enforces this constraint in particular, but there's a lot of similar constraints. So you can enforce these kind of parent-child relationships. You can enforce that if you instantiate a component, it must be given particular props of a particular type. So it's a really nice combination for React, React Native, Angular, all this stuff, and pretty much works out of the box.
What kind of projects do you think can benefit the most from TypeScript?
Yeah, so personally, I use TypeScript for everything from the smallest projects, little scripts and stuff like that. It just gives me a little bit more confidence that they're going to work when I run them, all the way to the biggest projects. So TypeScript is used internally at Microsoft, at Google, Slack, so really big companies. It kind of gets to the core of gradual typing, and I think we're going to talk more about this later, but kind of this trade-off between typing things dynamically and typing them statically, and both have their use cases. I think the bigger your project is, the more benefit it will get from TypeScript, but I use it for everything.
Is that why the subtitle of your book is called JavaScript that scales? What does it mean to scale in this case?
So I think it means a couple of different things. So one is it will scale across more lines of code. Another is it will scale across more engineers. And another one, it'll scale across more devices. So taking that one at a time. So more lines of code. If you have a bunch of code, so you have a big code base, if you're a big tech company, you have millions of lines of code, maybe you're a little bit smaller and you have tens of thousands or hundreds of thousands. At some point, your code is going to start breaking when you start making changes to it. And the reason is it's not totally clear when you modify something what else it's going to affect. And static types really help solve that problem. So they give you certainty that when you modify a line of code or the API to some function or some kind of module, you know exactly what else it's going to break, at least for certain classes of errors. It also helps scale across more engineers, so it's documentation. When you add little type annotations to functions, so you have a function f, it accepts a number and returns a string. That's a form of documentation for the function. And it replaces some doc blocks that you might be writing. And then the last one is it'll scale across more devices, because once you start scaling to services and start writing multi-threaded JavaScript, you very quickly run into the problem where unless you have well-defined protocols, your communication might break. So one device might send a message making one set of assumptions, a different device might be on a different version or make a different set of assumptions, and it might not quite work well together. So TypeScript is one of many tools that lets you type both sides of that communication, which helps give you more confidence about any kind of protocols.
When you say scales across platforms, what's an example of that?
Let's say, as an example, you can write TypeScript that runs on your browser. You can also write TypeScript that runs on the server, let's say Node.js.
In that case, if you had a function in the API in your Node.js application that you're calling from the web application, you could have more confidence that you're using the right set of parameters because you had the type information on both sides. Is that right?
Yeah, that's exactly right. There's a bunch of tools that do this, but at a high level, typically how it works is either you have a common source of truth that you compile bindings for both the client and the server, or for multiple servers. Or you have a source of truth on the server that you then compile bindings for the client. So instead of kind of independently writing API endpoints on both sides, so on the server, let's say you implement a REST endpoint, on the client, you make some assumptions about the parameters that endpoint accepts. Instead, you're going to compile a function, you're going to generate a function for the client side that you can then call. It's important to note TypeScript itself doesn't do that compilation. So it's not going to take your server-side endpoint and compile client-side code for it automatically. But there's a lot of tools that do it. And one way, because we're targeting JavaScript, TypeScript is kind of a natural language to express these kind of contracts in.
I want to move on to how TypeScript works. And this gets back to what you said before about how TypeScript compiles to JavaScript. But you also mentioned that JavaScript can be run through the TypeScript compiler. And I was always under the impression that JavaScript is an interpreted language, but it sounds like that's a mistaken assumption. Can you explain how the compilation process works and walk us through what the TypeScript compiler does?
Yeah, let's maybe take a step back first, if that's okay, and talk about JavaScript a little bit. So the way JavaScript works is JavaScript is an interpreted language, but that doesn't mean that if you write some JavaScript code, put it in a text file, feed it into your browser, let's say Chrome, and then run that JavaScript, it's not just literally running that code. There's a bunch of steps in between. This is something that's changed a lot over the years. It depends on the exact platform that you're running on, let's say, V8 or some other browser or some other engine. But between being a text file and actually being run by the browser, you're going to compile it to bytecode, or you might compile it to machine code. So there's still this compilation process. It just happens in a lazy way where you don't do it ahead of time, but you do it right before the user actually executes the program. With TypeScript, this stays the same. And kind of the beauty of TypeScript is it's one of these languages that targets JavaScript. There's many languages that do it. TypeScript is just one of them. But because it targets JavaScript, you can run it on any platform that supports JavaScript. And the way that TypeScript does it is it takes code and then it outputs JavaScript code, which you can then run as you would have run before.
You wrote that changing type definitions of a TypeScript program won't change the compiled JavaScript output. How is that possible, and what does that mean exactly?
Yeah, this is really important to forming a good mental model of how TypeScript works. So TypeScript is just JavaScript plus some types. The types will never affect the output of the program. So you can fiddle with the types all you want. You can make it safer. You can make it less safe by using different kinds of types. But in the end, the generated JavaScript output will look exactly the same.
If, for example, I had a TypeScript program that defines some types, like let's say I defined some classes and then changed the definition of those classes, but it continued to compile, then you're saying that the generated output would be identical.
Yeah, that's exactly right. So the types affect type checking that the TypeScript compiler does before it compiles. But either way, it can still compile your code. Even if it doesn't type check, even if the types don't totally work, it can still compile. Of course, if you want to opt into more safety, TypeScript has a whole bunch of different safety flags. One of them is a flag that controls this behavior and will not emit code unless the program type checks.
That part is actually the most difficult part for me to understand, how it can compile the code even if it doesn't type check. Maybe you can drill into that a little bit more.
Yeah, I think the key insight here is that the types will never affect the generated output. So it doesn't matter what the types are, they could be complete gibberish. They shouldn't be, because that's kind of giving up some of the benefits of TypeScript. But whatever the types are, the program will still compile. So TypeScript looks at the value level of your program as opposed to the type level. So essentially the JavaScript part of it, not the TypeScript part, in order to compile it. The types are just used for type checking, which is the step it does right before it compiles it.
If the type checker is giving me some information that it didn't type check correctly, it's still compiled, but it was telling me that it thinks there's an error in my program, then what's the step that I would take, or how would I respond?
So when you write TypeScript, you're going to get errors right in your text editor, assuming that editor supports TypeScript. I think this is every big editor out there. So VS Code, Atom, Sublime Text. As you type, you get little red squigglies right in the IDE warning you that you made a mistake. And as an engineer, there's different ways that you can configure your project. I recommend in most cases setting up your project in such a way that unless there are no red squigglies, the code doesn't compile. So you should really listen to the type errors because they're pointing out very likely mistakes in your program that you should probably fix. But if you want, you can ignore them. So as an engineer, if there are any kind of errors in your program, it's going to be surfaced right as you type code. So as soon as you type the error, you're going to get a little red squiggly underline under that error in your IDE, and then you can fix it on the spot.
I want to move into a TypeScript paradigm. What is the big idea or paradigm behind TypeScript?
I think the big idea behind TypeScript is that the types are there when you need them, and they get out of the way when you don't need them. TypeScript supports all sorts of different paradigms of programming. You can do functional programming, you can do object-oriented, you can do imperative programming. You can let TypeScript infer all the types for you, or you can specify them explicitly. It's sort of up to you. And TypeScript interoperates with JavaScript. It works well with all of these styles of programming. I think the idea is that the types are fun and they're useful, in that it shouldn't be tedious to fix them.
If we want to understand types in TypeScript, what's the best place to start? Is it structural typing? Is it classes? Or where do you want to begin with that?
I think I would maybe start with a high-level overview of the type system itself. So maybe how does the type system work, and then what are the kinds of types that TypeScript supports? So TypeScript, it's a fully structural type system. I think as your listeners know, this is as opposed to a nominal type system. Different languages are split on this. Some languages are a mix of structural and nominal. Some are fully nominal. Some are fully structural. So TypeScript is almost fully structural. And the reason it does this is because JavaScript is fully structural too. So you have a JavaScript function. It takes maybe a few different types of arguments, and you don't really know what you're going to get beforehand. So one thing you might do is check the arguments, and you might inspect it, and you might say, if the argument's a number, do this. If it's a string, do this. And likewise, maybe if the argument's an object, you might check some fields on the object to see if they exist. If some set of fields exist, do this. Otherwise, do this other thing. Because this is so common in JavaScript, the way to model this with static types is with a structural type system. And it works remarkably well in practice. The second part of that is that TypeScript's type system is static, which means that verification of types happens at compile time. That's before you actually run the program. So in just raw JavaScript, you can add runtime type checks. So you can say, if the type of this thing is a number, then proceed. Otherwise, throw a runtime exception. With TypeScript, these kind of errors are surfaced to compile time. So for example, if you have a function, you specify the types of the arguments. If the actual arguments that you pass don't match those types, that's an error at compile time. So that means you don't actually have to run your program to know if you did something wrong. The other aspect of the type system is that it's strong. And that's strong as opposed to weak. It's not a value judgment about the type system. All it's saying is that, for example, in JavaScript, if you try to add an array and a number, the result might be a string, because JavaScript is trying to do the best it can to coerce the types at runtime to match the intention you had as a programmer. So maybe as a programmer, you mistype something. JavaScript is going to try to do its best to make sure that works. TypeScript isn't quite as flexible, because if you're adding a number in an array, that's very likely a mistake. So TypeScript takes the opposite approach, where it tries to catch these kind of mistakes as early as possible. And that's why we call it a strong type system. The other part is that it's inferred. So there's very few things in TypeScript that you have to specify explicitly. If you have a function and the function has parameters, the parameter types you have to type explicitly. Most things other than that are inferred. So for example, function return types, the types of local variables, all of this will be inferred by TypeScript.
In your book, you talked about a concept called assignability. Is that something related to static type checking or TypeScript being strongly typed?
Yeah, it is. So let's do like a hello world of this. So you have a function f. It takes some argument that's a string, and you call f with a number. What should happen here? If this was JavaScript would try to do the best it can, and it would take this number and proceed as if you didn't pass the number, because it doesn't know any better. But with TypeScript, if you annotated the parameter as a string and you passed a number, TypeScript is going to perform a assignability check. So it's going to check, hey, is that number assignable to a string? Number and string are types that are not related, so it's going to fail. So that's going to be a little red squiggly in your text editor as you typed it saying, hey, you passed a number. Did you mean to pass a string? On the other hand, in most cases, it's going to work because you did the right thing. So if your function takes a string and you passed it a string, that's going to work correctly.
You explained that in TypeScript, types exist in a hierarchy, and at the root of this hierarchy is a type called any. What's the role of the any type?
Yeah, that's right. So there's a type called any in TypeScript. Any you should try to use as little as possible. It's essentially a trapdoor. TypeScript gives you a ton of these trapdoors. So if you don't want to write the perfect program, you don't want to think through the types right now, you can just mark something as an any type, and that'll let it through. So again, going back to the world's simplest function, it's a function that accepts a number, and you pass it some kind of value of type any, that'll be okay. In general, you should try to avoid it. And again, TypeScript has a whole bunch of compiler settings that'll ban this kind of behavior for you. And in any big code base, you should avoid this. And you probably should ban this kind of stuff. But otherwise, there's a whole bunch of assignability rules that TypeScript checks when it decides is something assignable to something else. So essentially, when you expect some kind of value, is it okay to pass this other value? And most of the time, it's pretty intuitive. So if you have a function that expects, let's say, a number or a string, and you pass it a string, that's okay because a string is a number or a string. But on the other hand, if you expect a Boolean, you can't pass it a class, anything like that.
You mentioned gradual typing and that TypeScript is a gradually typed language. Please explain gradual typing.
Yeah, gradual typing, it's this idea that your program might be composed of code at different levels of safety. So some of the code might be totally untyped, so no, meaning no static types at all. And then some of the code might be totally covered with types, so no any's, nothing like that. The compiler knows all of the types at compile time. I was researching a little bit. I think one of the first languages that are gradually typed was ActionScript, and that's, I think that was back in 1998. And Avik, the guy that works on Flow, which is another compile to JS language, he actually worked on ActionScript back in the day. In addition to ActionScript, there's a bunch of these languages that are gradually typed. So Google Closure is an example, TypeScript, obviously. Hack out of Facebook is another one of these. From what I could find, these gradually typed languages mostly come out of really, really big companies. They have really big code bases, like millions of files. And I think it comes out of this practical thing where you find yourself in a situation where you have a big JavaScript code base and you're not quite sure what to do with it. Because initially, it was really nice to have everything in JavaScript because it meant that you can move really fast and you can iterate quickly because you didn't have to wait for type checking to happen. You didn't have to add types to everything. But at some point, it became a liability because it not having these types also meant that you can't iterate as quickly anymore. And now when you make a change, you have to be so careful not to break anything else. You have to make sure to write a ton of unit tests, to do QA, to smoke test your app. And I think it also meant that it's hard to scale across a lot of engineers. So these big companies found themselves in a place where they had these existing really big code bases. It wasn't practical to totally rewrite everything at once, but it was really, really important to get more safety because it became a liability. And that's, I think, where these gradually typed languages came from. So TypeScript is a really great example of it. But again, it's one of a few, and it's a really modern phenomenon.
Let's go back to this idea of structural typing. If I define a function as accepting a certain type, you said that because TypeScript is structural, I think that implies that I can give that function another type that doesn't have the same name, but it would still be accepted by the compiler as a valid argument. Is that true?
Yeah, I think that's a good way to think about it. The mental model is if you need some type, any type that behaves the same way is okay. It doesn't have to share the same name.
Okay, so if it had to share the same name, that would be nominal typing versus structural.
Yeah, and it actually goes pretty far. So maybe one of the unintuitive bits of TypeScript is if you have a function that needs some kind of class, let's say an instance of class A that has a few members on it, and you pass that function an instance of class B that has the same types of members on it, so the same fields with the same types on those fields, that's okay by TypeScript. Because like JavaScript is duck typed, so TypeScript tries to inherit this behavior and it tries to model that statically.
Duck type being if it looks like a duck, walks like a duck, and quacks like a duck, it's a duck.
Right.
In a language like Java or C Sharp, you would have to have some kind of interface, and you'd have to say that both of those types shared the same interface, and the function accepted a type of that interface in order for that to work. But in TypeScript, you don't need to explicitly declare that they share the same interface.
That's right. It could be good practice for documentation for other engineers working on your code base to make a shared interface anyway, but it's really up to you. If there's not going to be a behavior at runtime, TypeScript isn't going to complain about it. TypeScript tries really hard to complain about things that would be real errors and to stay out of your way if you're doing something, even if it's a little bit weird, but that wouldn't result in an error.
What is type refinement?
Type refinement is a really interesting behavior of TypeScript. TypeScript is one of a small handful of languages out there today that have this kind of behavior. I think the best way to think about it is to start with an example. So let's say you have, back to this function f. It accepts either a number or a string, and the way you indicate that in TypeScript is using a union type. So it looks like number, pipe, string. That's how you're going to annotate that in a function. And then inside of the body of the function, let's say you want to do different things depending on if the argument was a number or a string. And the thing that you would do in JavaScript is use a type of check. So if type of argument equals and then number in quotes, do this. Otherwise, do this. And TypeScript is smart, so it understands this at compile time. And it knows that in the body of that if function, the argument must be a number. And if there is a return statement, it implies that outside of that if function, after that function, or after that if block, the argument must be the other type. It's a pretty convenient behavior, and it lets you model a lot of JavaScriptism. So a lot of JavaScript APIs are designed in this way where something might be a union of things, and you kind of, as you process this thing, you're going to refine it. And depending on what type it actually is, you might have a different behavior.
Let me just double check my understanding. You're saying that even if I declare my function to take a less specific parameter, in your example, a union type, as I progress through my function, the compiler can actually know that in a later block of code, it's definitely a more specific type. And from that point forward, it can treat that variable as that more specific type.
Right. So just as a programmer reading through that function, you understand intuitively that if you're doing a type of or instance of or in check, inside the block, it's going to be one type and not the union of all the possible types. TypeScript understands that too. So it tries to encode this intuition in the type checker itself.
Is that information something that is only relevant or only available at compile time, or is that somehow, can that also be made available at runtime? And is there any use for that?
Yeah, so something like if you're using a type of check, for example, this is something that will be available at runtime because type of is a runtime operator. It's just a regular JavaScript type of check. So if you have if type of argument equals number, then do something. That code will remain after TypeScript compiles your program because this is value level code. There's actually no types in there because you're comparing the type of the argument to a string. So it's either the string or the string number because it's just a JavaScript check. TypeScript is smart enough to understand it, but this code will remain in place after you've compiled it.
Okay, but would I be able to use user-defined type from TypeScript at runtime? So for example, if I defined type foo, would I be able to do a type of foo and compare, or is that not available at runtime?
That's a good question. So all the types in TypeScript are stripped away as you compile. So after you compile, none of the type information is left. So if you used, let's say, the type keyword to define a type alias for foo, this would not be available at runtime.
So you mentioned type aliases, and we talked about classes. So these are both examples of types. What's the difference? Maybe we can get into what's the difference between what's a type versus a type alias versus an interface. How are they related? And how are they different?
Yeah, so going back to what I was talking about before, I mentioned type level and value level earlier. Some parts of a TypeScript program are written at the type level, and some of them are written at the value level. Value level is it's all the parts of the program that's valid JavaScript code. Those are values. These are things that exist at runtime as you run your program. These are things that exist in memory. Everything else is only used at compile time. There's a bunch of things that are only used at compile time in TypeScript, and these things are created using the type keyword, the interface keyword, and then there's a few other ways to create types. So you mentioned classes. Classes declare types, but they also declare values. So if you have a class A that creates two types actually, so it generates a type for the instance of the class A that you could then use to type a function. Let's say you have some function that needs an instance of A. If you use the class keyword to create a class A, and then that has some methods, has some properties, etc., you could then use A directly in that function's parameter list. So you can say you have some function f, and it takes some argument of type A, and that means the instance of class A. And then when you use the class keyword, the other thing that it creates is all the static members. So if you had some static methods on the class, you can retrieve that using, again, the type of keyword. So TypeScript kind of reuses this type of keyword so you can fetch that again.
Is it just a difference in the way that you declare a type, or are there different kinds of types, whether it be an interface, a type alias, or a class?
In TypeScript, you can express a whole bunch of different types. So, just, little laundry lists. You can do number, string, Boolean. You can do arrays, tuples, classes, objects. And all of these, there's different ways to express them in the type system. In order to express them, you can either declare it inline, or you can name the type so that you can reuse it across multiple places. And it's sort of similar to how in JavaScript you would use a value inline, or you can assign it to a variable. So you can reference that variable from multiple places. So there's different ways to create a type in TypeScript. You can declare it inline. You can use the type operator to make a type alias. You can use the interface keyword to create an interface, or you can use a class, which will also create a type. All of these are pretty much interchangeable, and depending on what you need and depending on the type of class that you need, you can use the appropriate one. Let's say you have a function f and it needs some class A. So one thing that you can do is you can use the class keyword to declare a class, so class A, and then little curly bracket, maybe implement some properties, implement some methods, and then you would declare a function f whose argument is of type A. The other thing that you can do, because TypeScript is structurally typed, it thinks about classes a little bit differently. So what is a class? It's a thing that can be newed, N-E-W, newed. So you can make a new instance of this thing. So the way this works is, let's say you have this function f, and it takes some argument. You can say the argument is something that you can call, that you can new, and that'll return an instance of A.
Having played around with TypeScript a little bit, what I noticed you can do is you can declare a function, and if the function has a parameter that has some kind of structure, let's say it's an object that has a string property and a number property, you can just declare, in the declaration of your function, you can just give it something that looks like bracket foo colon string bar colon number, and that's good enough. Then basically I can give that function any argument with that same shape.
Exactly. And then if you want to reuse that same shape in a different function, if you want, you can pull it out just like you would pull out a variable in JavaScript. And the way you can do that is, there's kind of two ways. So one is you can use the type operator. So you can say type my object equals curly foo colon number comma bar colon string. And then you can update your function to say this argument is of type my object. And equivalently, you can use the interface keyword instead of the type keyword to do the same thing. So you can say interface my object curly foo colon string bar colon number, and it'll work the same way.
How would you consider the choice between the type alias the first way and the interface the second way? Like what would cause you to choose one over the other?
I think they're very similar. There's a few very nuanced differences. In practice, pick the one that you like stylistically the best. I personally prefer the type keyword. I know some programmers that prefer the interface keyword because they're coming from OO languages.
The type keyword does give you some options, like you can do I think an intersection or a union of different types. Is that something that's available on for interfaces as well, or is it limited just to type aliases?
So something like that is limited to a type alias. An intersection, if you're not familiar with it, it's let's say you have two object types, A and B. One object type has one member foo that's a number. The other one has a member bar that's a string. An intersection of those would be an object type representing foo number bar string. So an object that has both properties defined. So with the interface, you could also express this. And the way you would do that is using the extends keyword. So you would define an interface for one, and then an interface for the other one that extends that first one. And that's, in practice, it's very similar to what the intersection operator would do, which looks like an ampersand. There's some things that you can't express using interfaces. So this is unions, for example, aliases to primitive types. So for example, let's say you have a type A equals number. So it's just something that you use for readability or for documentation. You can't do that. So interface is just for object types.
Where would the union of two types be useful? Like, what would be an example?
This is something that comes up fairly often in JavaScript. Let's say you're defining a jQuery API. I don't know if anyone uses jQuery nowadays, but let's say you have a jQuery API and it's an animation API, and it takes some options. And let's say either you can pass it a single number representing the duration of your animation, or you can pass it an object with some more details. And let's say that object can have a property duration that's a number and type that's a string. And when you use your jQuery plugin, you can use either one of those. So you can either pass a number or you can pass this options object. And at the type level in TypeScript, we would represent this as a union. So you would say it's number, pipe, and then this object type with curlies.
Okay, so it gives you some flexibility in saying I can accept something that looks like this or like that.
Yeah, that's right. So as you're explaining this to yourself or to another programmer, if you'd use the word or, sometimes a union can be a good way to model that.
Another type of structure that you deal with a lot in JavaScript is JSON, and that seems to be something that other type systems struggle with. At least in my experience, it's difficult to work with JSON in Java, for example. How easy is it to work with JSON? Can you impose some type of type safety on it when you're processing something like JSON?
Yeah, so as long as you've typed your API, you're going to get the types for free. So I talked about this a little bit earlier, but there's all these, there's a few different tools that you can use to generate these type-safe APIs for you, which essentially it'll generate TypeScript code for you, which then makes sure that the API is type-safe. Of course, if you're using just raw JSON, so let's say like the fetch API or something like that, you can just cast it to the correct TypeScript type. And from then on, it's totally safe. So you've carved out this little unsafe island, and everything outside of this island is really safe. As long as you've done a good job of typing this boundary, then the rest of it's going to be safe. And of course, JSON, it supports a lot of the same types that TypeScript does. So you can model objects, arrays, strings, numbers, booleans, all this kind of stuff in TypeScript. It's super succinct.
There's one little feature that was convenient. I thought in JSON, you have a lot of properties, but you can actually say something meaningful about the key in the property. Could you explain how that works? Or maybe I'm not using the right terminology, but there was that little bit of syntax that makes it convenient for working with properties.
Yeah. So if you have a JSON object, there's some properties that it might have. And with some APIs, it might also take additional properties that are optional. So you might say that there's a property A that's a number, maybe a property B that's a string, and then any number of other properties that are booleans. And that's totally okay in TypeScript. So you can model that using an object type and then something called an index signature that models these additional types of properties. And then TypeScript also has operators to model optionality. So if the field may or may not be defined, all of the stuff that you might see in JSON, you can model using TypeScript type system, and it's really built for objects. So it can model it really succinctly.
I want to talk about interoperability between TypeScript and JavaScript. What more can you say about interoperability?
Yeah, so in modern JavaScript programs, you're going to be using a whole bunch of code, right? And it's often a criticism of the JavaScript ecosystem, but it's also kind of nice. JavaScript is a very modular language. So something that you might do is you might have a bunch of first-party code, and then you might also install a bunch of stuff from NPM, so a bunch of third-party packages. Some of these packages might be written in TypeScript. Your code may or may not be TypeScript. It might also be a mix of JavaScript and TypeScript. So when TypeScript was designed, this is one of the use cases it had to support. This is so common in JavaScript programs that it's really important to be able to use whatever packages you want and for it to work correctly. And if these things were written in TypeScript, then you also get the benefit of type checking. You get nice auto completion in your text editor. All of that comes for free. So the way TypeScript works is you can use JavaScript from TypeScript. And by default, when you import a JavaScript module in TypeScript, it's any. And if you don't want any's in your program, so personally, I don't, in a lot of big code bases, again, like at Google, so you use a TypeScript compiler flag to ban this. So what you do is you create this thing called a type declaration. And essentially, it's like a header file for the JavaScript package. And it models the outward interface of this package. For most third-party code that you might use, it's already available. So there's this namespace on NPM called @types. And usually what you can do is, let's say you install, let's say Lodash. You can then do npm install @types/Lodash, and that'll install all the type declarations for Lodash too. So you can then use it safely from TypeScript. You can also write these type declarations yourself in the rare case that it's missing. But TypeScript is such a big ecosystem, you're probably going to find it already. But sometimes you don't want it. Sometimes you're just prototyping something really fast. Maybe you're using some really exotic package that no one has written type declarations for yet. So what you can do is you can just turn off the safety flag in the TypeScript compiler, import this package, and use it. It's going to be any, so you're not going to get the benefit of static type checking, but you can quickly prototype stuff.
Is there a way to isolate those parts of the code that have less strictness, or maybe where you don't have the type information available?
Yeah, you can certainly do that. TypeScript is built to be practical. So one of the things that you might do is you might want to interoperate with JavaScript code. You might even start with JavaScript code and then gradually migrate the code base to TypeScript. And this is a really common pattern. This is something I've done at past companies. I think a lot of people that are switching to TypeScript are going to be in this boat where you have a big JavaScript code base and one piece at a time you're going to move it to TypeScript. So the way that works is you just rename your file to have a .ts extension. It can still use JavaScript, and that's okay. And what you can do is you can opt that part of your code base into these strong safety guarantees. So for TypeScript files, don't allow any's, but then for JavaScript files you're importing, it's okay to have any's, for example. And over time, as you migrate more and more of your code, you might want to flip on these safety settings one by one. There's like a dozen or so flags for safety to make your code more and more restricted, and you have stronger and stronger guarantees that you're doing the correct thing at compile time.
Would one approach to this be if you had a not necessarily a really large program, but a sizable enough program that you could break it into modules? Would it be useful to put stuff that wasn't type checked into one module? Or let's say you had some dependencies you didn't have type information for. Could you isolate that into one module and then just export some type of type safe interface to import in the other part of your program?
Yeah, that's certainly something you can do. I think it'll depend on your particular code base. Most often, actually, I'm not sure if I've seen people do this module-based approach. I think usually your other code is just .js files, and the code that you've migrated is .ts, but it's all part of one code base. But certainly, if you want, you can split your code into modules and then have different levels of safety for each, or even migrate a module at a time. But I think the more typical path is migrating just a file at a time.
But at the project level, you can only have one setting for compiler options, like whether or not you'll allow any. So then if you don't modularize, there's a trade-off in how much strictness you can apply to the project overall.
Yeah, I think that's a good way to think about it. At its core, TypeScript is a gradually typed language. What gradually typed means is the language might have 0 types, or it might be fully typed, and these things have to play together. They have to interoperate. But if you have untyped code in your system, it limits the overall safety of your system. So it might not be as safe at compile time as it might be if all your code was statically typed. But this is one of the nice things about TypeScript is that you can migrate a piece by piece. And then once you've migrated everything or the critical mass of your code, you can turn on these stricter settings to enforce that things are correct at compile time.
In episode 248, Axel Rauschmeier on JavaScript and ECMAScript 6 we talked about how some existing tools like Babel can compile one version of JavaScript into another. Can you please explain how these other tools coexist with or can be used together with TypeScript?
Yeah, so TypeScript does two things. It's a compiler and it's also a type checker. The type checking is something that only TypeScript can do. The compilation is something that other tools like you mentioned Babel, they do it too. And compilation is something like you have ES 2018 JavaScript or 2019, and you want to compile it down to, let's say, ES6 JavaScript. So older browsers or maybe an older Node.js runtime is going to support it. You can do that with TypeScript compiler itself. For bigger projects, I recommend just using Babel. There's a couple different TypeScript plugins for Babel, so you can just plug it into your existing setup and it'll just work.
Does that mean that I don't explicitly run the TypeScript compiler, but that's something that Babel takes care of as part of its process?
Yeah, that's right. There's a few different plugins, so there's a few different approaches to it. I think the typical setup is you're going to use the Babel plugin. It's going to run both the type checking and the compiler for you in parallel to speed it up a little bit. So you're still going to get the benefit of red squigglies in your text editor when you do stuff that's invalid, but then Babel still handles compilation like it did before.
Is there any other topic that you wanted to cover that we didn't talk about yet?
Maybe one is null as a type. I think that's somewhat unusual. So everyone's heard this famous quote that null was the $1 billion mistake. The problem is null is a type. It's a value. It's also a value that a variable can be, but it's something that remarkably few type systems model at the type level. Some things might be nullable, some things might not be nullable, and it's important to handle the cases where they might be null. Otherwise, that's often a runtime exception. So in Java, that's a null pointer exception. So in TypeScript, null is actually a type. So you can say a value is either a number or null, or let's say you have a non-nullable value, you can say it's just always a string. And it's important to make this distinction because if something can be null, it's really important to handle it. And TypeScript will verify at compile time that you've handled all the nulls.
Does that mean that if I declare a function with parameter type string and then I try to pass it null, it's going to fail at compile time unless it can verify that value is definitely not null?
Yeah, that's right. Or if you have a function that's a string or null, it's okay to pass it a string or null.
When you say string or null, is there special syntax for that, or it would just have to be the type alias or interface would have to say that it was string or null with like a union notation?
Yeah, it's just a union notation. So it's a string, then the pipe character, then null.
That reminded me of something that I read somewhere, that the majority or maybe even the vast majority of runtime errors in JavaScript are type errors. Does that mean that the goal, in a sense, is to get rid of, like, eliminate that class of errors? Is that what ultimately you're trying to do with TypeScript?
I think that's right. There's as a programmer, you have limited time in the day and there's all this code you have to write. And we're just humans, so we make a whole bunch of mistakes. And some of these mistakes are easy to identify. Some of them are a little bit harder. They might be architectural issues that, take a design review and, take sitting down with your team to really walk through and understand. So TypeScript prevents the really dumb mistakes. It's the mistakes that could have been caught, but weren't because you weren't using types. And it makes it super easy to do that.
Good. I think that's a good place to wrap things up. Just for final thoughts for our listeners, I wanted to make sure that we said something about your book. Could you please tell us about your book?
Sure. So it's called Programming TypeScript. It's O'Reilly's first book about TypeScript. I've been working on it for the last couple of years, mostly nights and weekends. I'm pretty proud of it. So check it out. It's on O'Reilly Books, also on Amazon.
It's definitely worth checking out. Is there any other resource or a place where listeners can find out more about you and the work you're doing?
I would check out GitHub. So on GitHub, I'm at bcherny, BCHERNY. If you also want to learn more about TypeScript without paying for the book, check out the TypeScript handbook. It's pretty good. But if you really want to go into depth, I'd suggest you check out the book.
Great. Thanks, Boris. Thanks for being on Software Engineering Radio.
Thank you, Nate.
For Software Engineering Radio, this has been Nate Black. Thanks for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.